We reach to the page 695. The last topic of this chapter is about the aromatic hydrocarbons. The definition of aromatic hydrocarbons is given at the top of the page. Aromatic hydrocarbons have 6-member carbon rings and delocalized electrons. Benzene is the primary aromatic hydrocarbon. So the base for all of the hydrocarbons comes from the benzene. But what is the benzene? The structure of the benzene is shown here. So it is a 6-carbon ring which has 3 double bonds inside that one. So I will draw the structure of the benzene here. It has 6 carbon in the ring. So I draw this 6 carbon. So it forms a hexagon shape. And we have 3 double bond in the structure. So you can see for each carbon atom, 3 electrons are shared, one with the double bond, one with the single bond. So they need to share one more electron to become octet. That's why each carbon bonds to one hydrogen atom. So this is the structure of benzene. This is uncondensed structure. But we said we have delocalized electron inside the benzene ring. We say that we have delocalized electrons because the location of these double bonds and the position of them are not fixed. These electrons can rotate inside the ring. So this one can go here, this one can move to here, these electrons can move to here. So I can draw another Lewis structure for these benzene. So benzene has resonance structure actually. I'm drawing another resonance structure for benzene here. In this case, the double bond are in these positions. So you can see the only difference between them is the location of the double bond. And actually, neither of these two are exactly the correct structure for the benzene. The correct of the structure of the benzene is average between these two structures. We can show the average by the circle inside the benzene ring. So I can draw the carbon here. Again, each one of them has one bond with hydrogen. And those delocalized electrons, I can show it by the circle. This is the better structure for the benzene, and it shows that the electrons which are in the double bond inside the ring are not fixed in their position, and they distributed on all of the 6 carbons that we have here. So this is the better structure for the benzene. Usually we show the condensed format of the benzene, so you can see in a lot of the text that the structure of the benzene is shown like this one. So a hexagon with a circle inside that represents the benzene ring. And as I have told you before, at each corner we have carbon atom, and from the bonds that we have, we know that for each carbon atom there must be one hydrogen. So this is the structure of the benzene ring that you will see in a lot of textbooks. You have these two methods of the drawing for the benzene ring here in your book. So this one, it shows the condensed format. Here is only shown the skeleton structure. So this circle represents the delocalization of the electrons. What is important about the carbon, because these electrons are delocalized and it move in the benzene ring, or is better to say it belongs to all of the carbon. All of the carbons inside the benzene rings are equivalent. So we have 6 equivalent carbon-carbon bonds inside the benzene ring. If these structures was correct structure for the benzene, then you would have 2 types of the bonds inside the benzene ring. One of them is the double bond that you can have here. The other one would be the single bonds that you have in this position. In that case, You have stronger carbon double bond carbon and weaker carbon single bond carbon bond inside the benzene ring. And you know that carbon double bond carbon is shorter, carbon single bond carbon is the longer bond, so you don't have the same bonds inside the carbons. But when we look at the benzene ring, we have 6 equivalent carbon-carbon bonds, which shows that all of these carbon-carbon bonds are exactly the same, and that suggests that we have resonance structure, and the real benzene molecule is what I have drawn here. We have the delocalized electron. Therefore, the benzene contains 6 equivalent carbon-carbon bonds, and the structure of the benzene ring allows electrons to be spread through the delocalized p orbitals over the whole ring. We have this structure on figure 212 at the right side of the page. This picture clearly shows that these electrons inside the p orbitals are distributed in all the ring all over the 6 carbons. So we cannot say that these delocalized electron belongs to which carbon. It actually belongs to the whole ring. So this is the structure of the benzene. All other hydrocarbons are derivatives of the benzene. So that's why we say the benzene is the base structure for the aromatic hydrocarbons. For example, look at this structure which we have here. One methyl group is there instead of the one hydrogen. You must know that at these positions we have the hydrogen, but we usually don't show the hydrogens that we have there. Okay, so we have hydrogens at this position, but at this position instead of having hydrogen we have a methyl group. So this structure is called methyl benzene. So we refer it to the base structure of the aromatic hydrocarbon. Here I draw another structure for the aromatic hydrocarbon. Okay, this is the structure of the another aromatic hydrocarbons. You can see that in all of them you have this benzene ring inside that. How we can name this one? Same as the naming of the other hydrocarbons, we need to know what are our branches. We have 2 branches here. Both of them are methyl, but what is the location of that? We have to number these 5 or these 6 carbons inside the benzene. This is carbon number 1, carbon number 2, carbon number 3. So one of them is in the first position, another one is in the fourth position. If you number it from the other side, this would be carbon number 1, carbon number 2, carbon number 3, carbon number 4, carbon number 5. So you can see in this case, one of them is in the first position, the other one is in the 5th position. So we choose the green method of the numbering, which the branches receive the smaller number. So the name for these aromatic hydrocarbon is 1,3-dimethyl, because in the first and third position we have methyl group, and the parent is benzene. Now let's answer some of the questions that we have here in the formative assessment for section 2. The first question says, list the basic structure features that characterize each of the following hydrocarbons. Alkanes. You know that in the alkanes we have only single bond between the carbons. Alkenes, ENE, we have at least one carbon double bond carbon in the structure. For alkynes, YNE, we have at least one carbon triple bond carbon bond inside the structure. And for aromatic hydrocarbons, we have a benzene ring inside the structure. Question number 2 says draw all of the condensed structural formulas that can represent C5H12. And question 3 says give the systematic name for each of the compound in your answer to the item 2. So we want to answer these 2 questions together. So I draw all of the isomers for this molecular formula C5H12. The first isomer which I can draw is the straight chain hydrocarbon. But before drawing the structure, we must identify if this molecular formula belongs to alkane, alkene, or alkynes. You can see the relationship between the carbon and hydrogen is CnH2n plus 2. So this suggests that I have the alkane hydrocarbon. So I'm drawing the alkane, which I have only single bond between the carbons. So the first one, let's draw the straight chain hydrocarbon. Okay, so this is the 5 carbon. For the first carbon, I need 3 hydrogens, so CH3. For the second carbon, I need only 2 hydrogen. Then I need 2 hydrogen. For the next one, also I need 2 hydrogen. And for the last one, it has already wall bonds, so we need 3 more hydrogen. So this is the first isomers for C5H12. The next isomers, I have to put the branch here. So on the second position, I put the methyl branch, CH3. Then I have the carbon. So this carbon, second carbon, it needs only 1 hydrogen. So I have CH here. The next carbon, I have CH2. The next one, I have CH3. So it's no matter if I put this methyl group here or on this position. In both of them, it's in the second position. If I put on the left side, when I number the hydrocarbon, I should number it from the left. It becomes 1, 2, 3, 4. If I put on the right side, when I number the hydrocarbon, I should number it from the right side. 1, 2, 3, 4. So in both of them, the methyl would be in the second position. So these two structures which you can see here are actually the same structures. We have only rotated the molecules. The next isomer which I can draw for this molecular formula is in this way. So I have a parent of 3 carbons, then I can have 2 branches, 2 methyl group connects to the carbon which is at the middle. So the first carbon at the left side, I need 3 hydrogen for that one. The carbon at the center, we don't need any hydrogen for that because it's already have 4 bonds. But the carbon at the right side, we need 3 hydrogen. So this is another structure for C5H12. Now let's name these isomers. The first one, which is a straight chain, is pentane. For the next one, which we have branch, we have to find the parent, which is the longest chain. Then we have to number that one. We have numbered it from the left side because the branch receives a smaller number. Then we name the branch. It's methyl in the second position, so we have 2 methyl. And the parent has 4 carbon, which is butane. So exactly the same name for the hydrocarbon which is written at the right side. It's 2-methyl butane. For the next one, the longest chain is this one. So this is our parent. We have 2 branches here. Both of them are methyl and it's on the second position. 1, 2, 3. So here we have 2 dimethyl. And the parent with 3 carbons is propane. So these are the isomers for C5H12 with their corresponding name. Question number 4. Give examples of property or use of 3 hydrocarbons. 3 hydrocarbons means alkane, alkene, and alkyne. And we had the example for each one of them and the usage of them. On page 689, you have examples for alkane in this table in figure 2.6. For example, we have gasoline as an example, we have kerosene. So these are the examples of the alkane. For example, the alkane with 36 and above number of the carbon, we use them as an asphalt. The alkane with 20 to 36 carbon, we use them as a lubricating oil, we use them as the waxes, and so on. Also on page 688, you have the name of the alkane. The first four alkanes are very famous. We use them for the cooking and for warming our houses. So these are another example for alkane. On page 693, we had an example for alkene and alkynes. The example for the alkene is ethene, which we use them as a hormone for the fruit ripening. The common name for that one is ethylene. And an example for the alkyne is given here. The ethine, which the common name for that one is acetylene, and we use it in the welding torches. When we mix it with the oxygen, we call them oxyacetylene, which we use for the welding because they produce a lot of heat when we burn them or upon the combustion. Okay, let's come back to the questions that we had here. Question number 5, we have done it earlier and it's available in the previous videos. So let's go to question number 6. It says write the structural formula of an alkane, an alkene, and alkyne that have 5 carbon atoms. Why are these 3 hydrocarbons not considered isomers? Here I'll draw them. So the alkane with the 5 carbon atom is C5H12 because the relationship between the number of carbon and hydrogen is CnH2n plus 2. For the alkene, the molecular formula is CnH2n. The number of the hydrogen is the double number of the carbons. So if we have 5 carbons, the number of hydrogen would be C5H10. And for the alkyne, the general formula is CnH2n minus 2. So if we have 5 carbons, 2 times 5 becomes 10, minus 2 becomes 8. The number of hydrogen would be 8. And the molecular formula is C5H8. Now I draw the condensed structure for each one of them. Let's draw the straight chain hydrocarbon for each cases. So for this one we have CH3, CH2, 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 CH3. For the pentene, this one is pentene. It would be CH2 double bond CH, CH2, CH2, CH3. And for pentyne, the last one is CH triple bond C single bond CH2, CH2, CH3. The first one is pentane because we have only single bond. So they are not considered isomers of each other because they have different molecular formula. And if you remember the definition of the isomers, we said the isomers are the compounds which have same molecular formula but different structure. Here we have different structure, but their molecular formula are also different from each other. So they are not isomers of each other.